Hi, welcome to Chapter 10, which is on multivariate time series modeling. Multivariate time series models are important because just like in multiple linear regression, sometimes we need more than one variable to be able to make good predictions of a dependent variable. The same thing is true in time series modeling. A lot of times you have another variable that's related to the process or the topic at hand, and having that second variable can be very instrumental in getting good forecasts. So that's why it's important. Happens a lot in economics. You have heard of the term leading economic indicator. Well, that is an example of a second variable that could be very valuable in a time series model. That's why we need to cover this carefully. Chapter 10 has two pieces to it because there are two types of multivariate model that we'll look at. One is MLR, multiple linear regression with correlated errors. That's what this video is about. And then later on, there'll be a video about the second type, which is VAR model. That stands for vector autoregressive model. So let's move on and talk about this topic for this video, which is MLR with correlated errors. Okay, this example is example 10.1 in your textbook. It's called business sales. There's a data set in TSWGE called B sales for business sales. I've got this code highlighted here. I've even got the plots down here below, so we'll just look at that in a second. But here's what we have. Sales, that's what we're trying to predict. Predicting sales. Sales, everything is in thousands, so sales is one. Now, how do we predict sales? Well, advertising expense could be very valuable in predicting sales. Now, notice we've got two different types of advertising. We've got TV advertising and we've got online advertising. Both of those could be valuable in predicting sales. Not only that, but we've got a third independent variable called discount, and the amount of discount of maybe a promotion with various discounts. That could also be very important in predicting sales. So we've got these three independent variables trying to predict this dependent variable of sales. Now in this example, you'll see that not only do we want to look at these three variables, but we also want to look at lagged versions of each of those variables. Meaning that last month's advertising expense, or maybe even 2 months ago, may have more effect on today's sales than an advertisement that just happened yesterday, because maybe enough time hasn't passed for it to take effect. So that's why these lags are super important to look at it in various ways. Okay, so when I plot those four plots, here's what we end up with. Upper left would be sales. When I look at that, I don't really necessarily know how to describe that pattern. Upper right would be advertising, TV advertising. Lower left would be online advertise. And lower right would be discount. Notice that so the first three patterns kind of look all the same. I can't make much out of them. They definitely look like time series data sets and plenty of randomness about them, no doubt about it. But if I were to try to look at plots 2 and 3 and say, oh, I can see how that relates to sales, I can't do that. Now, plot D, the fourth one, has a very non-random pattern about it, and that makes sense because someone at the company is saying, all right, we're going to run this discount for a certain amount of time, then we're going to hike it up, then we're going to keep this discount the same for a while, then we're going to tank it down. So it's got a pattern about it that is more predictable than the other three. I don't know that I would call it predictable, but it definitely does not look like the other three and doesn't look like a random time series plot. So there's the data that we're working with here. Okay, here's what we're going to do next. We will do our first regression. Remember, MLR, multiple linear regression. We'll set the data to be B sales. Set our sales variable, add TV, add online, and discount. Then we'll do a linear model, just a regular linear model Not saying this is the best way to do it, but let's start there. So LM for linear model, sales is our dependent variable, that's the Y. Tilde, then here come your independent variables, add TV plus add online plus discount. Of course, plus doesn't mean sum, it just means include these three independent variables. And let's run that. And then look at the residuals. We're going to fit those residuals with an AR. We set that to be for P to go anywhere from 0 to 8, and we didn't let Q have a chance. We were just trying to model it as an AR model, which is fine. And it selects, you can see here, for P to be 7, right? And there are the phi coefficients for those 7 parameters. These residuals will be stored in MLR fit because that's what we named it. And let's do that. What we're going to do next is we're going to do an ARIMA. Remember what that stands for. ARIMA gives it the chance to be non-stationary. So autoregressive, integrated, moving average, right? That's a P, a D, and a Q, right? And you can see that coming into play here because ARIMA, then the data set called sales, that's the dependent variable, sales, that's Y. Then order equals C. Here's our P, D, and Q. P is 7 because that's what we were told by AIC.WGE. Q is 0, and so is D. And that is our order. And then we put these three together, C bind, so add TV, add online, and discount. And then let's run it, and we're going to get a table of values, coefficients, along with their standard errors. Now, strangely, we don't, for the first time in the book, first time in the text or in video, we don't have a p-value. So the software does not give us a p-value, but that's going to be okay. We're going to be able to estimate one, or estimate the significance of this t-statistic. And it is a t-statistic. Remember, in multiple linear regression, if you're looking for the significance of the beta coefficients, what do? You take that t-statistic, divide by, or you take that parameter estimate, divide by its standard error, and that's what gives you the t-statistic, right? Now, we're not going to have to worry about these AR coefficients. Those don't mean anything. Neither does the intercept, of course. What we care about are these three independent variables: add TV, add online, and discount. Now, just as I said before, we don't have a p-value. So what we're going to do is we're going to take this estimate of the parameter, which is 0.07, and divide by the standard error, and we get as an estimate of our t-statistic, and it's tiny. 7 divided by 0.07 divided by 0.34 is not even close to 0.5. So that's going to be a very non-significant t-value. So is add online, the same situation, negative 0.09 divided by 0.2. So is discount, negative 0.15 divided by 0.13. It's a little bit above 1, still very insignificant. And therefore, this model has not been very impressive. Just to confirm that our table values do what we thought they should have done, let's take a look at some plots here of those residuals. And remember, if it had been a good model, these residuals should look like white noise. Let's run that, and we can see right away that that does not really look like white noise. It's just, there's pattern about it. And notice that the sample autocorrelations many of them are well outside the limit lines. There's actually a sinusoidal behavior look to it. And so that's how we know for sure that we don't think that this is white noise. We also could do the Young box test, and remember the Young box test has for the null hypothesis of white noise. So that means that you're hoping for white noise. So you're hoping for a very high p-value, which is a little unusual. Seems like we're usually looking for low p-values, but we want a high p-value. Let's run that and see what we get. We get a very tiny p-value. So we can't reject. So we do reject the null, which means it's not white noise. That's for k equals 24. Remember the default is k equals 24. That's how we like to test this, is at k equals 24. We'll also do it for 48, and we get a similar response. Very significant rejected null. That's not white noise. That did not work. Well, maybe we should put time in. Maybe we should put a trend. Maybe time has something to do with it. So we'll let t go from 1 to 100. We do the same type of thing, except we add in for an extra independent variable t. And to save a little time here, we'll just go pretty quickly through this. We see that we get an AR with an order of 6, so p equals 6 when fitting the residuals. Let's do our fit equals ARIMA again and look and see what the table values do. And you see that they do something similar as before. Actually, though, t looks like that's the trend, the time variable, is 0.046 divided by 0.014. That could be, that's above 2. Anything above 2 we would consider to be significant. That one actually has a chance, but let's continue to see if we feel like this model as a whole is going to be very valuable. Add TV still is a very small t statistic. So is add online. So is discount. Maybe it's coming up a little bit, but it's just not that significant. Let's look at our plots again and see if we have anything that looks more like white noise, or maybe the sample autocorrelations have improved. I don't think so. We still have a similar look as last time, and we'll let the Young box prove that to us. Notice I didn't say this in the last one, but you've got to give the order of the AR for this, and we get a very significant result, which means that we reject the null, and that's suggesting that we do not have white noise. Let's do it again for k equals 48. Again, reject the null. This is not white noise. That says keep modeling. Well, as at the outset we had said, lagged variables would probably be a good way to go, and that's what we're going to do here. So for lagged variables, the way that we'll lag our variables, instead of doing it by hand, not really by hand, but there are a set of code that you could use to manually lag your variables, but you don't have to do that because you can use dplayer to help you lag, and all you do is interesting syntax here. So dplayer it's : lag b sales add TV comma 1. That says create a new variable that looks back 1. So that's creating lag 1 for add TV. Do the same thing for add online. Do the same thing for discount. Or it looks like we're not lagging discount. It sort of wouldn't make sense to lag discount anyway. Discount is something that's going to be pretty present, pretty current. So it doesn't make sense to do that anyway. Plus, the way that plot looked for discount, it's one that we're not having a lot of hope in the first place. So that is how we defined our lagged variables. And then we defined new variables. We're going to call add underscore TV1 our lagged advertising for TV, and do the same type of thing for online. We'll call it add underscore online 1. So we have new variable names, and they're the lagged variables. Now let's do linear model again, MLR fit, where we let sales, of course, be our dependent variable. Then notice what we're putting in for the variables. Add underscore TV1, that's the lagged variable, plus add underscore online 1, that's the lagged variable, lag 1, plus discount with no lag. Data equals b sales, and let's run that. And then let's fit those residuals. Looks like we have order 7. Now let's do the fit equals ARIMA, giving it order 700, and see what the values look like out in the table. Remember, we don't care about the coefficients AR through AR1 through 7. We don't care about intercept. Let's look at add TV, add online, and discount. Add TV1. Now look, when we take 3.43 divide by 0.6, that goes in like 7 times or something. That's a really, really significant T value. All of a sudden, this looks like a very significant variable. Same thing for add online, even more so. 8.11 divided by 1.24. That goes in nearly 7-ish times or something like that. A discount, maybe a little bit of, I don't know, a little bit above 2. Again, we're not too crazy about that variable anyway, just because of the plot. And it's not that impressive, especially compared to those 2 variables that we just saw. So this is looking better. Let's look at the plots now and see if the plots look more like white noise. Yes, possibly. I know that the way this is scaled, it's kind of hard to tell by that. That leaves no doubt. This appears to be white noise. All the values are definitely within the limit lines. So that's a good look. Let's try the Young box test. Again, we're hoping for high p-values, and we do get it. We get a p-value of 0.28. That was for k equals 24. Let's try k equals 48. The p-value is even higher, 0.63. This is looking like a more promising model. Why? Well, we added lagged variables. One last thing we could do. Remember we had put trend in before, and it was the only variable that was significant when we didn't lag anything. So it would be worth putting trend back in. Maybe there is a trend in this data set. So let's give it a chance. So we do the same type of thing we did before, except we're just going to add trend to this. Right here in this step. In this step right here, we say MLR fit equals LM sales tilde T plus, and then everything else is the same. So let's do that. Run that. Then let's let AIC fit the residuals, and it's going to pick a P equals 7. Then we'll do fit ARIMA, order 700, and look at the table. Again, we don't care about the ARs. We don't care about intercept. We do care about everything after that, though. So for T, that's the trend. Not T as in T statistic. That might be unfortunate notation. T as in the trend or time. 0.006 divided by 0.038, that's about 2. So that's borderline, really. That's borderline. I wouldn't necessarily say that that's super impressive, especially compared to add TV and add online. Those stay extremely significant. Add TV 1, add online 1. Those are lag ones, of course. Discount still hanging in around the 2 line. It's actually below 2 this time. Discount's not looking good. And really, T could go either way. So if we're a little bit uncertain, why don't we let some plots help us out here to help make a decision? Looks to me like the autocorrelations still stay in between the limit lines. Let's check the Young box test, hoping for things greater than 0.05, and it's 0.26. So we would not reject that null. That is support of white noise. Do the same thing for k equals 48. Stays up at 0.62. So really, this is a adequate model. There would be nothing wrong with this model. I guess you'd have to make the decision about whether to keep T or not. But it's not a bad model. But really, what we've learned from this example is, wow, including lagged variables makes a big difference, and is something that we should always think about. Now, the last thing. Here's a good question. Who was it that made up a lag of 1? We just made that up. I don't know if we made it up. Maybe we had already taken a peek at what I'm about to show you. But couldn't it be that maybe 2 time periods ago, we didn't define anything. Maybe, I don't know if this is in weekly data or monthly data. I forgot that. But, you know, 1 week ago versus 2 weeks ago versus 3 weeks ago versus 4 weeks ago, those could all have different impacts on today's sales. So how do we know that 1 week ago is what we should have looked at? Maybe we should have looked at 2 weeks ago. Maybe that would have even been better. Maybe looking at 3 weeks ago may have even been better. Of course, there's finally a point out there to where you wouldn't expect there to be much impact. But this is too judgmental. This is subjective. We need something to help us out, and that's what the cross correlation does. So let me show you some plots real quick of the cross correlation function. So CCF is what that stands for, cross correlation function. Add TV and sales, and it's really like an autocorrelation function, and you're just looking for a spike. And we see it. Remember, here's lag of 0. And the very tallest spike is back at -1. Well, that's exactly what we put in our model. And that was for advertising TV. Let's do the same thing for ad online. And we again see a spike at -1. That would make us want to put in a lag of -1. And let's check, just for fun, discount. Kind of the same strange looking plot. I wouldn't necessarily say, oh wow, look, there's the lowest point is back at -3. I'm going to put that in. Yeah, but it's not that much different than the ones around it. Discount's just a strangely behaving variable. But that's how the cross correlation function is a great, easy plot to plot. You just saw the syntax for it, and it can give you a hint as to where there would be a value that you might want to take a look at to be a candidate lag. So this is the topic of MLR with correlated errors. Really interesting and really valuable, and something, especially in economic type data, that's just one of them. Economics and finance would definitely have a lot of value in using this idea of multivariate time series. That's not the only thing. We're going to see an example next where it's about something non-financial, and that would be melanoma and sunspots. But that's for later. But I hope you enjoyed that. I hope that clears some things up. I know that was a lengthy example, but an important one, and I hope that helped. See you next time.